Hello and welcome to the Daily Space for today, Thursday, October 8th, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Those of you watching this video may have noticed that I appear to be white. Now, I will admit I am a very Caucasian human being. That said, we are using a new hardware configuration today, and my camera driver absolutely refuses to let me adjust the exposure. This is something we're going to continue to work on before I appear on camera again, but I have given up for today. So in the spirit of Halloween, I think I'm just going to resemble a vampire for today. That said, the science doesn't care about the exposure time used to image me. The science cares about the exposure times used to image the universe. Today's science is largely science that has resisted being understood as much as my camera has resisted having its exposure time set. Our science is the science of how star systems form and change the substance of the universe. At the most basic level, we struggle with questions like, how do stars and planets form? How do stars change the composition of the universe over time? For the longest time, by which I mean since we really started trying to model what's going on, we thought stars had to be well on their way to being fully formed, roughly 1 million years old or so, before planets really begin their formation process. In broad brushstrokes, our story said that the collapsing cloud of gas and possibly dust surrounding a protostar would, well, over time, become dense enough after the star had become dense enough to have nuclear reactions. So the core of this knot of material that forms a baby solar system would shrink and condense, and eventually the knot in the center would be hot and dense enough for nuclear reactions to begin, and that protostar would light up, beginning interactions with the falling material around it, pushing outwards with light pressure. Some of the material around the new forming star would eventually collapse into planets, and the solar system would be born. The exact details of this story have been unclear, and it seems that every new theory has been undone by the next set of observations. Well, today's newly published observations show that even this level of broad understanding was apparently wrong. New images from the Atacama Large Millimeter Array show evidence of a dust ring with gaps circling IRS 63, a protostar less than 500,000 years old. This is a young system. And that disk, it indicates that formation of a planet disk has been going on for some time. This coexistence of a forming planetary disk and forming stars seems to indicate stars and planets form side by side and are roughly the same age. This work is published in the latest issue of Nature and is led by Dominique Sagari-Cox, who writes, "We used to think that stars entered adulthood first and then were the mothers of planets that came later. But now we see that protostars and planets grow and evolve together from early times like siblings." Co-author Ian Stevens goes on to say, "These rings and gaps suggest that we are seeing the earliest evidence of planet formation, and that planets certainly start to form within the first 500,000 years, and probably within the first 150,000 years. Planets, especially planets like Jupiter, started their own formation at one of the earliest stages of the star formation process." Over time, it's my hope that observers using the Atacama Large Millimeter Array and other high-resolution systems that work in the infrared and radio will be able to observe systems spanning the entire planet formation process, eventually putting together essentially a film of star and planet evolution that may catch each stage through a different star system, but that allows us to see the entire process of a solar system's growth, the same way that walking the halls of a hospital will allow you to see human growth from birth to death in the myriad faces on the different floors. Better telescopes are only half of the equation, however, for better understanding our solar system. We also need computers that allow more flexible innovation of computer models. One common assumption in writing software to model our galaxies, for instance, is that we can treat them as though their metal content is constant over time. The thing is, we know the universe was formed with only hydrogen and helium and trace amounts of lithium and beryllium. Everything else, by definition, had to come later. With each subsequent supernova and with the breath of each star's wind, heavy elements have been added to our universe's mix of elements. But when we've modeled galaxies and tried to recreate the generations of stars that we see, we typically told our software to just assume that the metallicity of the universe is, at least galaxy by galaxy, constant over time, which it isn't. Which means we can't actually recreate the universe we see with our simulations. Now, using new software that allows metallicity and dust content to vary over time, a team from Australia's ICAR have been able to reproduce 7,000 well-observed galaxies. According to lead researcher Sabine Bellstadt, with this tool, we can now dissect nearby galaxies to determine the state of the universe and the rate at which stars form and mass grows at any stage over the past 13 billion years. It's absolutely mind-blowing stuff. This research appears in the journal Monthly Notices of the Royal Astronomical Society. Bellstadt goes on to explain further. Most of the stars in the universe were born in extremely massive galaxies early on in cosmic history, around 3 to 4 billion years after the Big Bang. Today, the universe is almost 14 billion years old, and new stars are being formed in much smaller galaxies. This research goes to show that we can't hard code any of the variables in our universe. We have to give our code the complexity the universe deserves if we want to understand things. Finally, we have a story of beautiful galaxy diagnostics, and I really do mean beautiful. We are always trying to find ways to understand systems by looking for the brightest things that are easy to observe in nearby systems that allow us to see fainter objects and thus build our way up to saying, if you see these bright things, that means all these fainter things are there too. In star clusters, for instance, we look at the brightest stars, and based on how they appear, we predict what the rest of the star cluster would look like were we able to see it with our telescopes, because faint stuff we can't see with every telescope. This is well understood how to do with star clusters. What we're still figuring out how to do is apply the same idea to galaxies. When we look at these systems, it turns out that we don't have to rely just on stars. We can also rely on planetary nebulae. In a new study of the elliptical galaxy M105, researchers have found that old metal-poor populations of stars are littered with planetary nebulae. In a new paper by J. Hartke and others, they find an excess of planetary nebula from 15 to 50 kiloparsecs out from the center of this galaxy. This green glow is diagnostic of an old metal-poor halo. And what's fascinating about this system is the bulk of the galaxy's stars lie within the inner 3 kiloparsecs of this system. So you have the bulk of the galaxy out to 3 kiloparsecs, and then out from 15 to 50 kiloparsecs is where this old population is lurking, littered with planetary nebulae. This is new research and has only been done with one galaxy so far. But this hints at the way stars can evolve and gives us one more tool that we can look for and say, if there's a halo of planetary nebulae, big objects that are relatively easy to see, we should know that that planetary nebula crowned galaxy also has a halo of metal poor stars. This is just elegant little research. And we're going to end with this beautiful story of planetary nebulae. This has been The Daily Space. Today's episode was written by me, Dr. Pamela Gay. Engineering is provided by Ali Pelfrey, and web content is produced by Beth Johnson. You can get a complete transcript, show notes, and see images related to each of our stories on our website, thedailyspace.org. We are a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to the generous contributions of people like you. Your bits, your subs, your patronage at patreon.com. They allow us to do pretty much everything we do, but there is a deficit between what we bring in every month and what we need to pay all of our bills. To try and make up that difference, this October 24th and 25th, we're going to be holding a 36-hour-long hangout-a-thon. And you don't have to wait until then to donate. Please go to CosmoQuest.org and learn about what we're planning for the Hangout-a-thon and consider donating today. Thanks.